Hello to everybody. This is the second lecture about the matrix algebra on the course of quantitative and qualitative data limited variables. And okay, we'll discuss about matrix operations, the transposition, and symmetric matrices. Okay, matrix operations. Okay, we define a sum. Then, for example, if A is a M by N matrix and B is a M by N matrix, and the element are I, E, J, and the element of B are B, I, J, then we can define a matrix that is A plus B, taking A, I, J plus B, I, J, at row E and column J. Then, for example, if we have a matrix like that, 1, 2, 3, 4, 5, 6, plus 1, 0, 1, minus 1, minus 1, 2. There is no space, but we need to sum element by element. Then 1 plus 1, 2, 2 plus 0, 2, 3 plus 1, 4, 4 plus minus 1 is 3, 5 plus minus 1 is 4, and 6 plus 2 is 8. Then we need to sum element by element, and we need to check the dimension of the matrices, because if the matrices have different dimensions, that, for example, we have a M by N, and here we have a K by Q, where K is different from M, and Q is different from N, then we cannot sum the matrices. And then we need to check the dimension, the dimensionality of the matrix. Then we define a scalar by a matrix. And for example, is if C is real and is a scalar, and then is a 1 by 1, and A is a M by N, and the elements are I, E, J, then we define C A as C multiplied by I, A, I, J. And what it means? It means that, for example, if we have 2 multiplied by a matrix done like that, 1, 2, 3, and minus 1, minus 2, minus 1, then we need to multiply this scalar by each of the terms of the matrix. Then, for example, 2 by 1 is the first element, then 2. 2 by 2, 2. 3 by 2, 6. 2 by minus 1 is minus 2, 2 multiplied by minus 2 is minus 4, and 2 multiplied by minus 1 is minus 2. And this is the result. Then we need, when we have a scalar multiplied by a matrix, then we need to multiply this scalar by each element of the matrix, and then we get the results. Another fact is to know what is a matrix by a matrix, and we need to understand what is the concept of conformability. We say that A and B are conformable if the number of columns of A is the same number of row of B. Then, if this is M by N, then the number of rows of this guy, that is N, has to be the same, and this could be different. Then, the number of columns of A has the same number of rows of B. And for example, when A and B are conformable, then we can define a scalar product on the matrices, and then we can define A multiplied by B, and okay, but okay, if A is, for example, a M by N, then the element is Aij,
and Bij is a generic element of the matrix B, that is n by k, then we can define the product as Ca multiplied by B, and this is Cij, that is equal to the sum, this is a difficult formula, k from 1 to n of A, I, k, B, k, j. Then we need to do the product row by columns. For example, if A is something like that, 1, 2, 3, minus 1, 0, minus 1, and B, and this is a 2 by 3, then we take a 3 by 2, then it's something like that, and we take 1, 0, minus 1, minus 1, 0, 2, and we want to multiply I by B. We can do it because are conformable, because this 3 is equal to this 3, then we can define A multiplied by B, and this is equal to a matrix 2 by 2 that is done like that. We need to multiply this element by this element plus this element by this element plus this element by this element. Then it's 1 by 1 plus 3 multiplied by 1, minus 1 is minus 3 plus 1 is minus 2. And this is the first element of the matrix. And then we need to do like that. Then the second thing that we need to do is to take this row and this column to calculate this object. And then is 1 multiplied by 0 plus 2 multiplied by minus 1, that is minus 2, plus 3 multiplied by 2, that is 6. Then is 6 plus minus 2, that is 4. Okay, again, in order to, this is a 2 by 2 matrix, because maybe I've not written before, but the dimension of C at the end is a m by k. Then, you know, it's like that disappears what there is in the middle on the multiplication. Then if this is m by n, this is m by k, it disappears, you know, the common elements then at the end, and at the end we have m by k matrix for the multiplication of A and B. And in this case, we have these three that are the same. Then at the end, we get a matrix that is a 2 by 2. Here we go. And okay, we multiply this row by this column. Then is minus 1 plus 1, 0. And this one is minus 1 multiplied by 0, that is 0, plus 0, plus minus 2, minus 2. And here we go. And we get this matrix that is the multiplication of A by B. I want to recall this stuff because it's important, for example, in this example, because usually this is a m by 1 matrix. This one has to be n by k, and this one has to be k by 1, because at the end we get the dimension of this multiplication that is m by 1, because we cancel, as we said before, the k's. And this is m by 1. Then, you know, all these results are useful also in the course of regression analysis. Super. Now we check what is the transposition. For example, if A is defined by Ij, then we say that A transpose, this is m by n, is a n by m matrix, Aj. Then, for example,
if we have 1, 2, 3, 4, 5, 6, and this we call A, what is A transpose? Is 1, 2, 3, 4, 5, 6. In a certain sense, we flip A and we put in the, for example, in the this is A11, this is A12, this is A13. Instead of A12, we put, this is the element that is called B21. Then, in certain sense, we flip the matrix, and then we get the result of the transposition. Okay, this is a very simple example, and there is a result that if we multiply two matrices, for example, A, that is a m by n, and B, that is a m by k, and we want to take the transpose, then this is B prime, A prime. And this is a result that we need, for example, when we calculate you know, some terms, when we try to find the results for beta hat with the results of the estimator OLS, then in this case. Then we need to do some calculation which we use these results. And these are true because this one, it will be a k by n, and this is a m by n. And then at the end we have a k by m matrix, and it's like that. You see, this is a m by n, this is a n by m. This is a matrix that is m by k, and when we transpose it's a k by m. Then it's correct. Okay? At the end we have a symmetric matrix. The symmetric matrix is a matrix A that is a m by n, is always a square matrix, such that A is equal to its transpose. Then, for example, if we have something like that, this is a matrix that is symmetric, because if we want to calculate the transpose, looks like that, because we have to flip these two elements in this matrix in order to get the transposition. But -1 is equal to -1, then everything is the same. And this is a symmetric matrix. Why we need to study the symmetric matrix? Because, for example, the variance and covariance matrix, for example, if we have a vector that is given by x and y, and these are two random variables, the variance of this random vector is equal to the var, of x and y is equal to sigma square x, sigma square y, sigma xy, that is the covariance. These are the variance of x, this is the variance of y, this is the covariance of x and y, and this is x sigma y x. But the results for random variables says to us that the covariance of xy is equal to the covariance of yx, and then for this reason these two elements are the same, and this is an example like this one, and then it's like a symmetric matrix. Okay, and with this we end the second lecture.